Welcome back everyone. In this segment of the lesson, we're going to be looking at some more problems and how measurement can help me solve them. So let's go to the board and have a reminder of what's on our concept map. Cool guys, so again we're just going to be looking at different ways that measurement can assist me in problem solving, and we're also going to have some more discussions on specific strategies for measurement questions. Cool. Everyone, we are now going to remind ourselves on what we do when we've got problems involving combined shapes. So for measurement problems, it is crucial that we consider the words of the question, because if we read the introduction to the question, there are often hidden pieces of information that direct me on how I can actually solve it. Then it's also very important to pay special attention to any indication that shapes, surface areas, or volumes have been removed from, not form, the whole. And lastly, it is very important to visualize the problem. So often these situations are depicting something that could happen in real life. So it can help for us to visualize the problem and see how it would actually make sense for ourselves. So let's have a look at the first example. So the diagram below shows a glass with a volume of 117 pi centimeters cubed and an inner diameter of 60 millimeters. So we know that the volume of this glass is 117 pi centimeters cubed and the diameter is 60 millimeters. Before I even go further to look at the question, we just have to remember that there's a bit of a difference in the units. We've got centimeters cubed, but my diameter has been given in millimeters. So because it's been given in millimeters, I'm going to change it to centimeters because my volume answer was expressed in terms of centimeters. So 60 millimeters is the same thing as 6 centimeters, and if that is my diameter, I know that my radius would have to be 3 centimeters because my radius is half of my diameter. So A is asking us to calculate the inner height of the glass, and then B is asking me to calculate the total surface area of the water that touches the glass if it is 80% full of water. So we can see that we've got this dashed line indicating the glass being 80% full of water. Let's go to A. So the volume of the glass is 117 pi centimeters cubed. The inner diameter, we've already said, is the same thing as 6 centimeters, and we've said that the radius is 3 centimeters. We need to calculate the inner height of the glass. So what I'm going to do is I'm going to replace the volume with what I've been told the volume is. So the volume is 117 pi. This has been multiplied by pi times my radius squared, which is 3 squared, and this is going to be multiplied by my height, which is missing. Initially, I can actually just drop the pi's because if I divide both sides by pi, they will cancel. So 117 will be equal to 9h. Then I'm going to divide my 117 by 9, which gives me 13. So the height of my glass is 13 centimeters. So the total height over here is 13 centimeters. Great everyone, so I hope that you're with me so far. I was able to determine what the height of the glass was because I was actually given the volume and I was given the radius. So by substituting into the volume formula, I was able to isolate my h. Let's go on to B. Great, so B is asking me to calculate the total surface area of the water that touches if the glass is 80% full of water. So I want to know what surface area of the water is actually touching the glass if 80% of the glass is full. So in the previous slide, we worked out that the height is 13 centimeters. So if I'm considering the water that's actually touching the glass, we can see it's the water that's touching the outer edges of the glass, and we can see that it's water that's touching at the bottom as well as the surrounding sides. So we've got the bottom and the surrounding sides. But guys, please note that the top portion of this glass, or the top portion of the water, is not actually touching the glass, because we can see that the surface of the water is not touching the glass at this point. So that top circle will not be involved in the surface area of the water touching the glass. Our traditional formula for surface area is 2 pi r squared plus 2 pi rh. But now my surface area is going to be equal to only 1 pi r squared h, because I only have one circle of water that is touching the glass. And this is going to be added to 2 times pi r, with 80% of the height of the glass being touched with water, because I know that the glass is 80% full. So now I'm going to fill in the values. I know that my radius is 3 centimeters, and I know that my height is 13 centimeters. So we are going to fill this into my calculator. So I've got pi times 3 squared plus 2 pi multiplied by 3 multiplied by 0,8 multiplied by 13. So the surface area of the water touching the glass is 224,31. And this is centimeters squared. Cool, guys, let's move on to the next example. So we now have a box with a rectangular base that is being used to carry cylindrical cans. So we can see we've got our box with its specific dimensions, and we also have our cans with specific dimensions as well. So we have been told that 90 cans have been placed into the box, and now we're going to be determining the volume of the space that is empty within the box. So we can imagine that this box has now had 90 cans packed into it, but we want to know how much space is empty. Could I possibly fit more cans? So at this point, I'm just going to pause. If I'm going to calculate the volume of the empty space, I'm first going to have to establish what the actual volume of the box is, and once I've done that, I'm going to have to determine what the volume of one can is, and then I'm going to have to multiply that by 90. So the volume of the empty space will be the volume of the entire box, and then I would have to subtract 90 times the volume of the cans. Let's go back to the board. So we've said that the volume of the empty box is going to be found, or the empty space is going to be found by first finding the volume of the box, then subtracting the volume of the 90 cans. So firstly, we have to actually see what the volume of the box is. I know that the volume of a rectangular prism is always the area of the base multiplied by the perpendicular height. So if I fill in my values, I've got length, which is 55, times my breadth, which is 31, multiplied by my height. So if I pop this into my calculator, I've got 55 multiplied by 31 multiplied by 30. And that's going to give me 51,150. So 51,150 centimeters cubed is the volume of my box. But now I need to actually know what the volume of my cans are, so I can subtract that from the volume of the box. Cool. And the volume of the 90 cans will have to be 90 times the volume of a cylinder. And I know that the volume of a cylinder is pi r squared times by h. So it's going to be 90 multiplied by pi, and my radius, so over here I can see that the diameter is 6 centimeters, which means that my radius will be 3 centimeters. So it's going to be pi times 3 squared multiplied by my height, which is 11. So let's plug this all into my calculator to see what the volume of 90 cans will be. So it's going to be 90 multiplied by pi times my radius squared times by my height, which is going to give me 27,991,59. So 27,000 guys. So we've got 27,991. And my decimal was 0.59. So we know that that is going to be the volume of the 90 cans within this box. So in order to do that, I'm now going to actually see how I can work out the empty space. Great, guys. So now that I have the volume of my box and the volume of the 90 cans, I can work out the volume of my empty space. Because I know that the volume of the empty space will be the volume of the box minus the volume of the 90 cans. So let's pop this all into my calculator. So we're going to have 51,150 minus by 27,991,59, which is going to give me 23,158,41. And we know that that is centimeters cubed. So that is how much empty space we have left. Now I'm going to ask you a follow-up question. Is if we now have the volume of the empty space, which we've worked out, and I want to figure out what the volume of any other cans that could fit into this empty space. So the follow-up question is, how many more cans can we add to this box? So if I consider the volume of one can, which is pi r squared times h, the volume of one can is 311,02 centimeters cubed, and the volume of the empty space is 23,158,41 centimeters cubed. So if we want to work out how many more cans we can fit in, I'm going to take the empty space and I'm going to divide it by one of the cans, because then I can see how many more cans I could possibly fit into the box. So let's go back. So we're going to have our empty space, which we've already got in our calculator, which is 23,158,41, and I'm going to divide that by 311,02, which is going to give me 74,459. But everyone, before I look at that decimal, we just have to think, can I put a fraction of a can into a box? No, I can't all of a sudden say I'm packing cans into a box. So hypothetically, I could only fit the actual number of cans left into the box, because I can't fit fractions or decimals of cans into the box. So let's go back to the board. Because my answer is 74,459 going on, hypothetically speaking, I could only fit 74 more cans into the box. But of course, this might not be possible, because it's all got to do with how we pack cans into the box, because obviously we have the dimensions of the cylinder, which may restrict us. So it's more just a question to think about, how much more could I do with that empty space? But we also have to acknowledge that there could be restrictions with that. Great, guys. Thank you so much for joining me for this measurement lesson today. I really hope to see you guys soon. Bye.